Hello everyone, I am Chukwuma Chinedu, and with Bracco Gerald, we'll be presenting our project which is titled Design and Simulation of a PV System to Meet All the Energy Needs of an Electric Bicycle. Here is the outline of our work. We'll begin with the introduction and literature review, and we'll end with our conclusion and references. Introduction and literature review. According to literatures, bicycles have existed since the 1890s. The increasing awareness of the negative consequences of emissions requires community actions from individuals by reducing excessive energy consumption and adopting sustainable ways of living. One such adoption is using electric bicycles to commute, which could help reduce environmental emissions. Also, electric bicycles adoption can help reduce parking problems, especially on campuses with cost savings due to lower energy cost per travel distance, especially when its batteries are recharged with PV or other renewable energy sources. Today, there are a lot of electric bicycle brands on the market with various specifications. For our work, we designed a PV system for Go City electric bicycle. Considering the cloudy weather in St. John's, we looked at the ability of photovoltaics to sufficiently provide the energy needs of an electric bicycle. Also, we considered the effects of temperature on the system. The simulation tools we used are Homer Pro, which we use for steady-state simulation of the PV system, and MATLAB Simulink for our dynamic simulation and modeling. System sizing and steady-state simulation. Here you can see the block diagram of our design system. The PV array block, which converts solar energy into electricity, and the charge controller block, which contains a DC to DC converter with additional controls to regulate the current and voltage delivered to the lead-acid battery. Between the lead-acid battery and the lithium-ion battery, we have another DC to DC converter, which efficiently matches the voltage levels for efficient charging of the electric bicycle's lithium-ion battery. We downloaded solar irradiation data for St. John's on Homer Pro. We also got the specification sheet of the Go City electric bicycle, from where we calculated the energy stored in its battery, and then we got the daily distance traveled by the rider using Google Map, and then calculated the daily energy consumption and annual energy consumption. Due to the nature of the light load we got, we selected a DC bus voltage of 12 volts and considered 5 days battery backup for days with cloudy weather, knowing that St. John's is always cloudy. Then we considered the depth of discharge for our system, and all this guided us in selecting our components on Homer. We now use Homer Pro to identify the most viable component sizes to supply the electrical needs of the Go City electric bicycle. And so you can see the schematic diagram of our setup on Homer with our PV connected to the DC bus bar, our battery connected to the DC bus bar, and our load to the DC bus bar. Here you can see our Homer Pro optimization results. We selected a PV array rated 150 watts on Homer Pro, and the result shows our net present cost is $1,708.83. Our levelized cost of electricity is $1.83 per kilowatt hour. Our operating cost per year is $29. Our capital expenditure is $1,334. Our renewable fraction is 100%. The capacity shortage is 0, and also there is 0 unmet electric load. Excess electricity is 30.9%. At this point, I will hand over to my colleague Gerald to continue with the dynamic simulation.
To be able to test the system design, we went on to perform simulations in Simulink. We began by modeling the dynamic system of the proposed PV solution. So based on the Homer results, we designed a charge controller and a battery charger. The charge controller was a buck converter with the specifications found on the left table, which included a power of 450 watts, input voltage of 22 volts from the solar panel, and output voltage of 13.4 to charge the lead acid battery, and then others. And now the boost converter, which was our battery charger, had a rated power of 240 watts with an input voltage of 12 volts and an output voltage of 52 volts to charge the lithium ion battery. Now this diagram was taken from Simulink, where you can see that we have the PV panel with its solar irradiation and then temperature, and then we have our buck converter that is taking the output of the PV panel and charging the lead acid battery. Now we have a switch that turns on. Whenever the switch is on, the lead acid battery charges the lithium ion battery. After completing the dynamic simulations, we realized that anytime there's a change in temperature or solar irradiation, the charging parameters are affected. Hence, we decided to go on to design a control system that can meet the requirements of the system. Our control system was based on PI controllers to improve the performance. Two parameters, which are the solar irradiation and temperature, were varied. And then we made sure that our PI controller was able to respond quickly to ensure that the battery charging voltage and currents are not affected by these parameters. Also, we made sure an overvoltage protection relay was used in this simulation for our protection system. Furthermore, we decided to test for a load change. That is whenever there's a power change at the output of the charger. And the results will be presented in the following slides. So here we talk about the system dynamic simulation results, where we monitored the voltages and currents of the lead acid and lithium ion battery for changes in temperature and in radiance. On the right hand side, we can see that as the irradiation decreases, the charging current also decreases, and then the state of charge reduces as well. Like the time it takes to charge fast reduces. Also, in the graphs below, you can see that as temperature varied from 25 to minus 15, the lead acid voltage was charging, but the current was also reducing as well, and the SOC was increasing. We also tested our boost converter, which is our battery charger, and then that is found on the right bottom side. We can see that the lead acid voltage is constant, and then it's charging the lithium ion voltage, which is also constant. The lead acid current is also constant, with the lithium ion current being constant. Now, because there's no control, there are a lot of ripples in the charging currents, which will be addressed in the control section. And now we can see that the lead acid state of charge decreases while the lithium ion state of charge increases. So after implementing our control system, we can see from the results displayed here that we varied the irradiation as time went on. And then we can see that based on the variation, looking at the lead acid voltage, it remained constant. The temperature was also varied, reduced from 25 to minus 10 degrees Celsius. The lead acid voltage stayed constant. The state of charge also stayed constant, and now the lead acid current at a certain point, which is below 400 watts per meter squared, the control system struggles to maintain the constant current. But we can see that as soon as we increase it to 800 watts per meter squared, the constant current for charging the lead acid battery was brought back to 15 amps in the right graph below. In this results, we are presenting the lithium ion voltages, currents, state of charge, and then the load change. So we can see that for the change in load, we realized that the lithium ion voltage was at 52 volts. As soon as we changed the load, the controller made sure that the constant voltage, which was 52 volts, was maintained within a short period of time. The same applies with the current. And now we can see that the state of charge is not being affected because of the robust control. So the state of charge is constantly increasing independent of the load change. To conclude, in this presentation, we proposed a PV system that can meet all the electrical needs of an electric bicycle in St. John's. And we first designed the system in Homer, and then we used the Homer results to design a dynamic model of the system in Simulink. Then we went on to build a control system to make sure this system is robust enough. And then we also proposed the results for all these control system simulations and the Homer results as well. We also ensured that our system could withstand could be very protective in the sense that it could withstand over temperature, over current, and over voltage conditions using relays that are activated whenever these conditions occur. And these are the references we used. Thank you for your time.